All right, so L'Hopital's rule is another way of evaluating limits. So if you think back to like the first quiz and stuff like that, we talked about how to evaluate limits, and there was like factoring and like, multiplying the numerator and the denominator by like the inverse of like the highest power on the denominator and stuff like that. So L'Hopital's rule is like another way that we can do that, or just evaluate limits in general. And this is what it is, and basically all it means is like, if you get an indeterminate form, and remember we talked about indeterminate forms, that was like 0 over 0 or infinity over infinity, like could be positive or negative, infinity over infinity, right? That was your indeterminate form. So L'Hopital's rule just says, all right, so if you've got one of those two things, then you just take the derivative, right, of the numerator and you divide it by the derivative of the denominator. Now, an important distinction that I see a lot of students mess up on is this is not the quotient rule, right? This is not like where f of x equals u and then v equals g of x and then you do that. No, there's no quotient rule here. It's just the derivative of the numerator divided by the derivative of the denominator. And honestly, the best way to learn this rule and get familiar with it is just do practice problems. I got a list of other indeterminate forms here, which we'll talk about in a bit, but let's just get to a basic example. So with like limit problems, right, you always want to try direct substitution first. So if we do that here, then we just get 4 squared minus 16 over 4 minus 4, which is, right, 16 minus 16, which is 0, divided by 4 minus 4, which is 0. So we get 0 over 0, which is an indeterminate form. You always need to try direct substitution first. You'll get points off if you don't do direct substitution first. But then now in this situation, and right, if we were doing like, if we didn't know how to do L'Hopital's rule, right, we'd probably, factor that binomial into x minus 4 and x plus 4, right? And then we would cancel out the x minus 4s and stuff like that. So, but with L'Hopital's rule, we just do this. I use an arrow and say LH. So we're still looking at the limit as x approaches 4, but we take the derivative of the numerator, derivative of x squared minus 16 is just 2x, right? And then we divide it by the derivative of the denominator. Derivative of x minus 4 is just 1, right? Because the derivative of negative 4 is 0, derivative of x is 1. So, and then this equals, right, just 2x, right? So we just got 2x. So then now we can do direct substitution, and we will get 8, right? Because we just plug in 4 for x, and we get 8. And if, we just did the regular x minus 4, x plus 4, right? If we just factored out this binomial right here to this form, and then canceled out these x minus 4s, and then we plugged it in, we would get 4 plus 4, which is 8, right? So we can see L'Hopital's rule, works. So now another example could be this. So limit as x approaches infinity. So the first thing we want to try is direct substitution. E to the infinity is just infinity, and then infinity squared is just infinity. So we get infinity over infinity, which is an indeterminate form, right? So we can use L'Hopital's rule to take the derivative of the numerator, derivative of e to the x is just e to the x, and then the derivative of the denominator, derivative of x squared is just 2x. And then we can try direct substitution again. And this is still the limit as x approaches infinity. Make sure you're rewriting your limit signs at each step. So then we try direct substitution again. E to the infinity is still infinity, and then 2 times infinity is still infinity. So again, we get an indeterminate form. So sometimes with these L'Hopital rule problems, you'll need to use it. You'll need to use the rule multiple times in order to get the result. And so if we use it one more time, right? So we use L'Hopital's rule on this limit as x approaches infinity. Derivative of e to the x is still just e to the x, and then the derivative of 2x is just 2. So then now we do direct substitution, and e to the infinity is still infinity, but divided by 2, infinity divided by 2 is just infinity. So we would get an answer of infinity here for this question. So sometimes you need to use it more than once. So then there's the possibility of other indeterminate forms. So this is a list of them. I feel like these two are kind of intuitive, like why they would be indeterminate. Like if you're subtracting infinity from infinity, right? Like one of those infinities has to be like bigger than the other infinity, right? So one of them is going to be pulling a little more. For this one, it's like 0 times infinity. 0, so like it's like this unit, you kind of need to like forget that 0 is a number, because 0 is like not really a number. It's like kind of just a number that we let behave like the idea of empty. So like 0, what is 0 times infinity? So 0 is an infinitely small number, right? And infinity is an infinitely large number. So it's like you don't really know which of those is like real. And then 0 to the 0, these I just kind of don't get. I mean, like, I don't get why, like, 0 to the infinity isn't, like, a indeterminate form either. But it's not. 0 to the infinity is just 0. So that's the only one that's not, like, here. But these are some of the indeterminate forms that you could find out. And the basic gist of them is through one method or another, if you get any of these as indeterminate forms, you can use algebra to somehow rewrite them as a numerator and a denominator, as a fraction, right? So all of these 5 indeterminate forms are algebraically reducible to, or reducible, reducible, are reducible to this f of x divided by g of x. So one of those examples is here. So if we do direct substitution here, we get 0 squared is just 0 times ln of 0 from the right. If you remember your graph of ln, right, it looks something like this. So as we approach 0 from the right, we're going down towards negative infinity, right? So 0 times negative infinity, same thing as 0 times infinity. And 0 times infinity, right, is an indeterminate form. So then we have to use L'Hopital. Well, actually, we have to reduce it to a fraction, and then we can use L'Hopital's rule on it. So this is indeterminate, and you would need to mark that. So then now we say, okay, we need to move one of these to the numerator and one of these to the denominator. So like we've got the yellow term and the blue term. So to start off, you can just try. And really, honestly, on a quiz or an exam or whatever, there's no harm in just trying to bring one down and leave the other up top. Basically, one of these, you have to choose to bring one term down in the denominator, and bringing one of them down works, and bringing the other one down doesn't. Generally speaking, bringing down ln x is always a bad idea. You should always try and bring down the other one first. So, like, if one way we could rewrite x squared is in the denominator x to the negative 2, and then that's all under ln x. So this is the limit as x approaches 0 from the right of ln x divided by x to the negative 2. And now this is in a form where we can use L'Hopital's rule on it, right? So we use L'Hopital's rule, and so then now we're talking about the limit as x approaches 0 from the right of the derivative of ln x is 1 over x, and then the derivative of x to the negative 2 is negative 2x to the negative 3. So now we can simplify this a little bit, right? So this is the limit as x approaches 0 from the right, and then we can bring down that x to be 1 divided by negative 2x to the negative 3 times x, which is the same thing as x to the negative 3 plus 1, which is the same thing as x to the negative 2, which is the same thing as x squared divided by negative 2. So this is basically limit as x approaches 0 from the right of x squared divided by negative 2. And we can just use direct substitution here. 0 squared is 0 divided by negative 2, and that's just 0. So our answer here would be 0. All right, so then this one, so if we do direct substitution here, right, so 0 from the right, so if we remember our graph of x squared, it looks a little something like this. So if we're going towards 0 from the right, we're talking about this, so we're going up to positive infinity. So we've got infinity minus 1 divided by sine of x. Sine of 0. So sine of 0 is just 0, right? And so 1 divided by 0, or I guess it'd be 0 from the right, so then this would also just be infinity, right? Because if it's 0 from the right and then we plug it in here, we keep that 0 from the right. So that would just be infinity minus infinity for the indeterminate form. So that's indeterminate. And generally, if you ever have a problem that looks like this, you're going to get infinity minus infinity for your indeterminate form. If you're subtracting two fractions and it clearly just doesn't work out, it's going to be infinity minus infinity. So then we need to somehow make this a whole fraction, and we're kind of going back again to like when we first started dealing with limits, where we wanted to find a common denominator, right? And one of the ways we can find a common denominator with this problem is to multiply this sine x by x and this x by sine x, right? So in order to do that, we got to multiply both the numerator and the denominator by the other one's denominator. So this becomes sine x divided by x sine x minus x divided by x sine x, right? So then we combine that all into one fraction, and we get sine x minus x, all divided by x sine x. So then now we've got a fraction that we can use L'Hopital's rule on, right? And I would say a pretty common question that people have is, do you need to try direct substitution again when you get it into this form? And the answer is no, because unless you've made a horrible algebraic error, this will be completely equivalent to this basic form, right? You're still going to get infinity minus infinity. And you could do that and try it, and you would get infinity minus infinity. The indeterminate form is not going to change until after we use L'Hopital's rule. So after we take that derivative of the numerator and derivative of the denominator, that's the only time that anything's going to change. So the derivative of our numerator, right, is, so still limit as x approaches 0 from the right. Derivative of sine x is cosine x, and the derivative of negative x is just negative 1. And then divided by x sine x, this is going to be a chain rule where we got u equals x, u prime equals 1, u equals sine x, and u prime equals cosine x. So then that becomes sine x plus x cosine x. And then we can try direct substitution again. And then we get, so that's cosine of 0 minus 1 divided by sine of 0 plus x times sine. All right, and so we do direct substitution here. This simplifies to 1 minus 1 divided by 0 plus 0 times 0, which is 0. And so then we get 0 over 0 again, which is indeterminate. But kind of like two problems ago, right? Don't be deterred by one indeterminate. We got to use L'Hopital's rule again. So now we're talking about limit as x approaches 0 from the right. And then so then now I'll highlight it. We got to take the derivative of the numerator here and the derivative of the denominator. So the derivative of cosine x is negative sine x, and then the in the denominator, derivative of sine x is cosine x. And then we got to take the derivative of x cosine x. We've got the red term and yellow term. So derivative of x is 1. Derivative of cosine x, derivative of cosine x is a negative sine x. So then this becomes negative x sine x plus cosine x, something like that. So then we try direct substitution again, and so negative sine of 0 divided by cosine of 0 minus x sine, minus 0 times sine of 0 plus cosine of 0. So then we can simplify this a little bit. Sine of 0 is just 0, cosine of 0 is 1, minus 0 plus, and again, cosine of 0 is 1. So that's 0 over 2. So that is just 0. Okay, so then the last one is going to be something like this. So, right, we would go and we use direct substitution. So this becomes 1 plus 3 divided by infinity to the 2 times infinity. So then this simplifies to 1 plus 0, right? Because any regular finite number divided by infinity is 0, and 2 times infinity is just infinity. So this becomes 1 to the infinity, which, as we said before, is an indeterminate form, which I don't really get, but I don't know. I probably just don't know enough about math, honestly. So we need to, and you can almost kind of let your logarithmic differentiation instincts kick in, right? Because we have an x in the base and in the exponent, and if you remember us talking about and this was even on exam 2, right? Like if you have an x or whatever your variable is in the base and in the exponent, then you got to use logarithmic differentiation. Similar concept applies here with L'Hopital's rule. So we basically say y equals the limit as x approaches infinity of 1 plus 3 divided by x all to the 2x. So then, kind of like we would with logarithmic differentiation, we just take the ln of both sides. So we've got ln y equals ln of the limit as x approaches infinity of 1 plus 3 divided by x to the 2x. And so then ln y equals, and for reasons I can only describe as extended PEMDAS, the ln moves inside of the limit sign. So then we're dealing with the limit as x approaches infinity of ln plus 3 divided by x all to the 2x. And we don't need that parenthesis. So then now, right, ln y equals limit as x approaches infinity. That 2x comes down just like it would if we were doing like logarithmic differentiation with this, 1 plus 3 divided by x. And so then now this is transformed into a problem like number 3, where we had one thing that we needed to bring down into the denominator and then one thing that needed to stay up in the numerator. So now we've essentially got that type of a problem, right? We've got the indeterminate form infinity times 0. Or wait, infinity, yeah. Yes, infinity times 0. Sorry. And then, so then ln y equals limit as x approaches infinity. So now we have to choose, do we want to bring down 2x or do we want to bring down this? And again, kind of like I said earlier, ln is almost always the wrong choice to bring down. There's a certain order, I forget what it is, of stuff you want to try and bring down. ln is almost always at the bottom of that list. You want to try moving down the 2x first here. So let's keep ln in the numerator. And then, so then this 2x becomes 2x to the negative 1, right? So that becomes, right, 1 over 2x just in the denominator. Actually, this would be easier to leave as 2x to the negative 1. So then what would happen is, and again, we don't need to use direct substitution again yet, because right now it's the same thing as we had when we had 1 over infinity. We just did some algebra to it to make it look slightly different. The only time we need to try direct substitution again is after we've used L'Hopital's rule, which we will do right now. So ln y equals limit as x approaches infinity, and just kind of forget about the ln and the limit as x approaches infinity for now. When you're talking about L'Hopital's rule and you're talking about limits, you're only talking about what's inside of the limit sign here. So, right, your limit kind of has parentheses, something like this. So when you're talking about L'Hopital's rule, you're only talking about limits. You're not talking about derivatives technically. So you only want to be touching what's inside of the limit. So what that means is we got to take the derivative of our numerator, which is this, and then the derivative of our denominator, which is this. So the derivative of ln of 1 plus 3x is going to be a chain rule problem where our outside function is ln of x and our inside function is 1 plus 3 divided by x. So derivative of ln x is 1 over x, derivative of 1 plus 3 over x. Derivative of 1 is 0, derivative of 3 over x is a negative 3 over x squared. And I guess that itself is kind of a chain rule problem if you wanted to break it down into that. Or just a reverse power rule, or you know what I mean. So then we need to plug this into the chain rule formula, f prime of g of x times g prime of x. So then that means we've got 1 divided by 1 plus 3 divided by x, all times that negative 3 divided by x squared. So then that is the result of our chain rule. So this will be our numerator. So here, let's move this shit over here then. And then our denominator is going to be, God, what a mess this problem is going to be. Then our denominator will be derivative of 2x to the negative 1. So that's a chain rule problem where our outside function is, what am I doing? Let's just write this as 1 divided by 2x. So, which itself is just like 1/2 times 1 over x, right? And we know the derivative of 1 over x is just negative 1 over x squared, so that becomes 1 over 2x squared, something like that. So then now, all right, so now we've used L'Hopital's rule, so now we can bring this all back together. So, right, we can bring this 2x squared back up into the numerator, and so we get this negative 2x squared times 1 over 1 plus 3 divided by x times negative 3 divided by x squared. And this is still ln y equals limit as x approaches infinity. Good God, this problem sucks. So then now we can try direct substitution again. So that's going to be negative 2 times x squared. Infinity squared is just infinity. Times 1 divided by 1 plus 3 over x, right? That's just 1, right? Because this would go to 0. Right, so, all right, sorry, this would go to infinity. This would go to 0, so that's just 1 divided by 1. Times, and then infinity squared is just infinity. So negative 3 divided by infinity, that's just 0. So then what we're dealing with is negative infinity times 0, which is an indeterminate form. And so we would have to take the L'Hopital's rule of this again. Unless I have made a grave error, this is just a beast of a problem. You guys get the idea. You just keep going until you get it. You probably wouldn't be given something this hard on the exam. I might have messed up. I'm not sure. We'll find out. See ya.